We're gonna do one more today, because it's tight. And again. So the experiments, and I've lost track of it, I think it was 2 through 5. We're looking at flipping coins and pulling cards out of a deck. And we did 2 kinds of experiments. We did until repeat experiments. And we did until all experiments. And one of these you turned in as an in-class quiz and you guys did great on. You'll see your grades on those when we send it back to you. Until repeats and until alls. Until a repeat, this was the one with the coins when I said flip until you get the same side twice. So if you want heads, tails, done. Tails, tails, done. Tails, heads, tails, done. Tails, tails, done. And we figured out pretty quickly that with this tree diagram, you could analyze what should happen over the course of flipping a coin until you get a repeat. And we analyzed that data. As a matter of fact, I still have it. Let me throw it up here on the board. Yes, exactly. Very nice. And you remember. Very good, very good. This guy in here. We're going to do another one of these experiments today with some more data. And this coupon collector. Morning! So glad you guys made it. We just hope you were safe. Makes me nervous. There we go. So here was the repeat curve that we got. We got almost as many 2s as 3s. You convinced me that that made sense. I still believe you. Because you looked at that tree diagram after 2 flips. And you said after 2 flips, you're either going to match the 2 flips, heads, heads, or tails, tails, and then be done. Or you're going to have one of each, which means on the next flip, you're going to match something that already happened. And I was happy with that argument. We got an average of 2.47. Do you remember how to calculate that average? Do you remember how to calculate that average? I'm going to keep asking you to do these kinds of averages from now till the end of the term. So please say yes and or tell me how to do it. Okay, Michelle, explain it to me, my friend.
Wasn't it like the frequency times the number of flips plus the next set of number and divide that by the total amount?
I love it. Perfect. That's called a weighted average. It's probably the most important thing you'll learn in this class. It is the kind of idea that will teach you how to pick a health insurance plan later. It's the kind of idea that will help you pick a life insurance plan or understand your car insurance better or understand if you should purchase extra insurance on a product. It's all based on a weighted average. It's the kind of formula, if you will, that Michelle just described, or procedure she just described, that will explain to you how long you can play in Vegas on average until you have no money left. Because you will have no money left eventually. I mean, eventually you'll run out. Why? Because that weighted average has a specific value for every game in Las Vegas. Every game of chance. Let me take that back. Every game of chance. I can't speak for games like poker and blackjack, because in games like that you have to know when to stop and when to play and when to trade out cards, and I don't know how to measure that because A, I suck at them, and B, I can't count that fast. But for games like roulette, which we'll analyze in here, I got a quiz plan for you guys. Craps, which we'll actually play in here. Chuck-a-luck, which we'll play in 243 if you take 243 later. All of those games have a predicted outcome. There's a certain field called an actuarial field. Being an actuary, their job is to set the guaranteed payouts for certain events, so the companies they work for don't go bankrupt. So when you guys pay your insurance bill every month, if you have one, there's a reason you pay that much. You've often heard the most expensive car insurance that you have to pay is for a 16-year-old boy. Right. 16-year-old boys. It's somewhere in there anyway. I might be getting the age wrong. There's a reason for that, right? What's the reason? As a biker, I can attest to this.
Statistically, they have more accidents, more claims.
Yes, statistically, they have more accidents. I can speak from a bike commuter's perspective. The only age group I have trouble with is 16 through 19-year-old boys. They're the ones that decide they need to roll the window down and say something to me. They're the ones that act surprised when I catch them. Get out of the car. It doesn't surprise me they have more accidents. They're more reckless behind the wheel on average. I was a 17-year-old boy at one point. I understand that. And I was very, very careful behind the wheel because I'm a dork. But that's okay, because on average, they're not. That's what Amy said correctly. On average, they're not. And that's why this average didn't come out exactly what it should have been. Remember what it exactly should have been? 2.5 exactly. Because half the time, if you look at your tree diagram, half the time, you're not going to get a repeat in the first 2 flips. The other half the time, you are. So if you don't get the repeat here, you're going to get the repeat next. Because if you don't flip a tail, you flip the head back here, that's a repeat. That makes sense? So half the time, we ended up in the 2, half the time in the 3, and I think our graph does a pretty good job of seeing that. We had slightly more on the 2 side than the 3 side, but that would even out if I had you keep flipping coins. Fair? But I sensed you were growing tired of that. So we changed over, and instead of doing until a repeat, we then did until all. Until has 1 L. There you go. Then we changed it, and I said, keep flipping until you have seen all the sides of the coin. And this is the results that we got. Beautiful results. I'm going to give Anya credit. She's not here right now, but she's the one that said it looks exponential. Does it look exponential? It does. It looks like an exponential decaying curve. Because you shouldn't keep flipping the same thing over and over again. It can happen. As we said, it can happen. They clump in and you get tails, 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 tails. But it gets harder for it to do that in a set number of flips. It's one thing, friends, to observe 6 tails in a row in a large chunk of coins. Let me see if I can explain that to you better. Okay, here's that demonstration I showed you guys last time, right? So, can you guys see a crazy run of tails or heads in here? There's 5 tails right there. What else we got? 4 tails. Okay, so let's flip it again. Any crazy runs in there? Let's see. Actually, nothing, I guess technically speaking, tails, 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 there's 5 there. How about here?
6.
Yeah, there's 6 there. How about here? There's 6 heads. How about here? Okay. Woo. So it's not, we got a big one. Oh God, yeah, there's like 8 heads in a row. So it's not hard when you're looking at 200 flips of a coin to go in and spot a clump, right? Here's what I want you to do next. Watch the first 5 cells and only the first 5 cells right here. Okay? Watch, just ignore everything else. As a matter of fact, here. There we go. Now, there's one. There's one. We're going kind of quickly now. You see, we're not getting one every time, are we? We're getting one roughly every 10 or 15, maybe 20. Statistics says we should get one every 16. We should get all heads or all tails every 16 times on average. That does not mean that every 16 we're going to see one. Every 16 we're going to see one. It's going to average out to every 16 times we'll see one. So it's a different story to see 200 coins flipping and go in and find a clump versus flipping a coin 5 times and finding a clump. That's a much harder thing to do, yes? Hopefully you see. Hopefully you see why. Good. If you don't see why, don't worry. We'll keep seeing it. Fair enough? Okay, good. Let's not save that. We'll keep all those 200. So this is what we got next. Shrink down a little bit more. Then we move to cards. This was the number of times we had to pull cards until we saw a repeated suit. This was part of the quiz you guys did on, I guess it was Wednesday? I guess it was Wednesday. Shuffle the cards up, throw a card, look at it, make a note of the suit. Take the card back in, shuffle up, deal again, make a note of the suit. Keep doing that until the suit repeats. It took, on average, 3.2 draws until we got a repeat. We've now moved past 2. We've moved past 2. We've moved past 2 because it's kind of hard to go hearts, hearts. It's more predictable to go something, something else, and then one of those 2 things. Does that make sense? That's what 3.2 essentially means. Throw clubs, throw something other than clubs, then the third card will match one of those 2 on average. On average, of course. Now sometimes it takes as many as 5. Remember why I topped out at 5? Remember why you couldn't go any further than 5? This was definitely a top end. Remember why?
Because there were 4 suits, so on the 5th card, it's going to be one of those suits.
Yes, ma'am. There's 4 suits in the deck. 4 suits in a deck. Worst case scenario is you throw hearts, you throw clubs, you throw spades, you throw diamonds. The next throw is going to match one of those 4. Has to, right? Has to. Fair enough? Good. Then it got super interesting. Then we said, let's keep drawing and dealing to ourselves until we've seen every suit. And this took one poor person 22 trials, and I apologize for that. It was awful. It was awful. That's why, one of the reasons I wrote the program that I shared with you guys last time. One of the reasons I wrote that program. So on average, do we ever do the average for this one? Should have it hidden under here. There it is. I got an average of 7.45. And now that I'm seeing that, that's what you guys got too. Because that's what I graded on your quizzes, 7.45. So it's going to take almost 8 throws until you see each of the suits. That's because they clump. If they didn't clump, it would take 4. It would average 4, right? If there was no clumping, it would average 4. You'd go 1, some other one, the last one. It would be the least. Now that ended up being the most common occurrence for us. But that's not the average. Remember how I taught you to think of the average on a graph like this? If you ever had to find the average of this graph, without actually knowing what the number was, and you guys did a pretty good job of this. Remember what you did with your hand? That's a plate of cookies. The bars are the height of the cookie. Where would you put your finger to balance the cookie sheet? And that's the thing. There's no method, there's no formula involved. Just figure out where you put your finger to balance that tray, if this was a tray of cookies. Don't forget that one's out there at 22. He's a very heavy cookie and he's very far out. So where would you have to put your hand? You can tell that you can't put it at 4. It's going to fall that way. You've got to balance it in such a way that balances the weight evenly. 7.45 will be right about there. Yeah? Now you guys guess between 8 and 9. Hell yeah, that's a good guess. It's hard to get precision like this, but you can get a ballpark estimate. You know it's not 4, and you know it's not 12. You guys did a really good job of getting within 1 or 2 of the true value. If you need more precision, do what Michelle said. Yes. Fair? Questions so far? Yeah, okay, maybe. I'm getting there. Now, we're going to apply it to dice. I brought dice, but you are not going to roll them. Oh no. Oh sweet Jesus, no. Because this can take far too long. Think about it. We had one poor person that had to draw 22 times until they saw all the suits. Imagine how many times you could roll a die until you saw all the sides. Right? It gets a little ridiculous. Now think about this experiment. Excuse me. Think about this experiment. This wouldn't be too bad with a die. Roll a die until you get a repeat. What's the maximum number of rolls you'd have to do if you were throwing a die until you got a repeat? You have to roll 7. Because worst case scenario, you get one of the numbers, then you get another number, then you get some other number you haven't seen, and eventually you've gotten 1, 2, 3, 4, and 5, and 6 in some order. The next roll has to match one of them. But this one is the one I'm worried about. That's the one I'm worried about for the die. So, we're not going to do it that way. We're going to do it with a program that I gave you guys last time. This should be on it. So, everybody do this. We've got a few more people here now. We're going to have to pair you guys up with somebody else probably to get the data for this one because it's going to be a little bit... I didn't bring the sharing cable if you have an 83. Turn them on. Press program. So turn them on and press the PRGM button. Last time I did share programs with a lot of folks. So chances are some of you have all these in there. Raise your hand if you've got the one that says coins because that's the one we have to use now. Okay, if you don't, get near somebody that does. And we're gonna have you guys work together. We're gonna have you guys work together. We're gonna collect data together. The rest of them are great, but we're not gonna need them right now. You will need this one for your last exam. FYI, I posted your last exam for you guys for week 11. Let's do a month from now. Let's do a month from now. You're welcome. Let's do a month from now because I want you guys to find the time to do it. Right? It's open. It's open. The Blackboard link's not, so you can't submit it yet. But it's not due till week 11. Just so you know it's out there. Cool? All right. Got Usain Bolt. It's got an MP3 player. It's got my drunk old lead singer. And something else. I think that's all. Oh, and craps! And craps! Some of which we'll do in class together. And then it'll make more sense. That last question will make more sense. You guys look terrified. It's not that bad. You got a
So
month to do
you're
it.
drunk, what did you say?
It's about my drunk lead singer drinking Red Bull at a show.
Oh.
And I was realizing, like, you know you're killing your liver right now. I'm like, you know what? Don't even worry about it. Drink it, drink away. I'll make a math problem out of it. So, anyway. Yes, problem with having a geek drummer. What are you drinking right now? How fast are you drinking it? Okay, if you have this program, highlight it like it is right now. You have to, it's probably the first thing, and just press enter. And then it says Pergam coins, and then press enter again. Now it should say sides with a question mark. What it's asking you to do is to put in the number of sides your coin has. The program is called coins. Anything can be viewed as a coin if the sides on that object are equally likely. For example, a coin is definitely a coin because heads and tails are 50-50. Pulling cards out of a deck and checking the suit is a four-sided coin because each of the suits is equally likely. So you could model that with this. Don't do that yet. Suppose you wanted to mark the rank of the cards in the deck, not the suits, but the ranks, the 2, the 3, the 4, the king, the jack, the ace, whatever. How many sides would that coin have? 13 sides. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Jack, queen, king, ace. There's 3 more plus my 10. 13 or 13. 13-sided coin. What would a 13-sided coin look like? I don't care. It doesn't look like anything. You can have a program to do it. That's the thing. You don't actually have to build one of these things. I asked my dad years ago, Dad, can you build me a 3-sided coin? He's like, sure. I'm like, but the kick is it has to come up heads, tails, and whatever the third side is equally likely. He hung up on me. It's very hard to do. And then he actually mailed me stuff in the mail that looked like 3-sided coins, but they don't come up 1/3, 1/3, 1/3. The heads and the tails come up too frequently. So just because something has 3 sides doesn't mean the 3 sides are equally likely. It's like saying, there's a 50% chance I'm going to crash on my bike on the way home today. Because I either am or I'm not. Well, that's not a good way of looking at it, is it? Because that's like saying it's a coin flip. But it's not a coin flip. Just because 2 things are equally likely doesn't, just because 2 things can happen doesn't mean they're equally likely. With a coin flip, it is. But sometimes, and you'll see this in 243, it's not 0.5, 0.5, but something like 0.9, 0.1. They have to add up to 100%, but oftentimes they're weighted differently, 0.9, 0.1. Why would you care about 0.9, 0.1? Anybody think of an example you would care about when it's 0.9, 0.1? Related question. Anybody keep chickens in here? Then you care about it. Because when you buy a chick at the store, you buy a pullet, huh? You buy a pullet, which is a little sexed female chick. I don't know how the hell they do that, but they do. They somehow sex them. They figure out that that one-day-old thing that's the size of an Easter candy is a girl. But they're only right 90% of the time. Which means it's 0.9, 0.1. Girl, boy. So yeah, just because 2 things can happen doesn't mean they're equally likely. I'm not going to crash with 50% probability. If I crashed 50% probability, number 1, I wouldn't ride to work, because number 2, I'd probably be dead by now after riding for 20 years. Fair enough? So, for these, they're going to be equally likely though. So, for us, we're going to simulate a 6-sided coin or a die. So type in 6, and then press enter. It's going to think a couple seconds, and then it's going to tell you it took 3 trials until you got a repeat. So maybe it went 1, 2, 1, or 2, 3, 3, or something. So it took 3 rolls of the die to get a repeat, and it took 9 until you got all the sides at least once. Fair enough? So what it just did was the same thing you guys did in class with the actual items, but it's doing it for you inside its little mathematical brain, which I love. One of my favorite programs to write was this one. Press enter again. It says, should I roll again? Should I change the die, or should I be done? Let's roll again. It's thinking. This time it took 4 trials until a repeat, and 15 until all sides showed. Let me know if anybody gets something interesting. I have 1 line of code written into this one that's very, very fun. Let me know if you don't get something that looks like this. Run it again. Let's keep running until somebody gets that outcome. Roll again. It took 3 and 13 this time. 3 and 13. You guys are probably getting different numbers, yes, I'm assuming?
Yes.
Good, you should be, because we're all randomized differently. Good. Keep doing it. 3 and 21. You can see this is why I don't want us doing it in class with real dice, because you'd be here all day, which is okay. Data collection's wonderful, but at the same time, it's also nice to see what's called a Monte Carlo simulation. Has anybody gotten the interesting outcome yet? Nobody yet. It's okay. Here we go. 3 and 29! Sweet Jesus. 4 and 26! Nobody's gotten it yet. Let's keep going until we do. You're basically always, usually, you're going to be getting these numbers. 4, 11, blah, 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 blah. But every once in a blue moon, what'd you get? 4 and 27. I got 2 and 19. Now, if you're always getting numbers here, it's totally fine. That's normal. That means that it took 2 until I got a repeat, which means I went 2, 2, or 1, 1, or something like that. And 19 until I got to see all the sides once. That's okay. And it could be 4 and 27. I mean, hell, it could be something like 5 and 82. I mean, theoretically speaking, it could take 82 trials to get a repeat. It could take infinitely many trials. It just probably won't. So here's what I want you guys to do now. And eventually somebody's going to get the weird outcome that I talked. You got one of each! There it is. I've written in the code to celebrate. I want to get so good. I'm going to keep going. I wrote the code to celebrate the one of each category. One of each means, what do you think it means? It's celebration. It's got an exclamation point, right? One of each! What does it mean? Don't overthink it. It isn't a math question. No! Ding! Thanks for playing. No, I'm going to say it because it's a die. No, it did happen here once, didn't it?
Create a paradox within itself.
Say that again.
Create a paradox.
Not a paradox, it's a true outlier. One of each. What does that mean, do you think?
It went back in time and...
You're overthinking this, Doc Brown, flux capacitor.
You got 2 and
Part
7.
is Dr. Who.
Oh, you can't get 7. Oh, no. Yes, wait, hang on a second. You're damn close, Mimi. You're damn close. You said 2 and 7, right?
Yeah, 2 and 6.
Meaning, you got exactly one of each of the sides. So it went, say, 1, 2, 3, 4, 5, and 6. Now, what would the numbers be in that case? You have to think about this. What would the numbers be if you rolled one of each of the sides? So I didn't say it came 1, 2, 3, 4, 5, 6, but if you got each one exactly one time, each of the sides of the die.
0 and something else. 7.
What? How many times till all sides showed? This is the easy one. 6, because you rolled it exactly 6 times and got one of each. What would this one be? You had to get a repeat,
13.
and you haven't yet. You rolled one of each of the sides, right? So you haven't gotten a repeat yet. 7. 7! Because you rolled one of each, you rolled 6 times. Whatever you roll next is going to match one of the ones that you already rolled. Does that make sense? Think about what Simi said before. It's the same logic. This will always be one more than the number of sides possible. Maximum. That's why it was 5 for the cards and 3 for the coins. That's why it's 7 for the... So if you get one of each... Thank you, Mimi, for keep going. There we go! If you get one of each with an exclamation point, it's a celebration. And the numbers are 7 and 6. So if you get that, just write down 7 and 6 for the trial. So here's what I want you guys to do. Do this a bunch. Do this a bunch. At least 10 times. But because it's so quick, you can do it you can do it a lot of times, yes? Since it's so quick, you can do it a lot. Run this experiment a whole bunch of times and make a little laundry list in your notebooks, and then we'll collate data together again, yes? So we'll go over here, and we'll just make it really simple. We'll do repeat, and then until all. And I've written the program that it gives you both up at the same time. So right now, I just did mine again, and I got 3 and 7. So I'd write 3, 7. And then I did it again. Now it's 3, 11. So I'd write 3, 11. And what I want to do is I want to collect all this data in and then graph it, yeah? And then see if we can extrapolate the pattern of how many it should take to get all of this. Fair enough? Good? Maybe? Ish. And you know what one of each means now. It's a celebration. It's a mathematical celebration.